Hello students, in the previous two lectures we discussed about bivariate expectation and also bivariate transformation. In this lecture we are going to discuss about sum of two independent random variables. Many situations arise where a random variable can be defined in terms of sum of other random variables. Therefore, we need some results about the properties of sums of random variables. Consider two independent random variables x and y. The sum of these two independent random variables, that is x plus y, is another random variable w. So in many of the applications we need to work with the sum of several random variable. One such example is adding a signal random variable with a noise random variable. Let the signal random variable be s and the noise random variable be v. Now when you add these two random variables s and v, we will be getting another random variable w. One more example for the sum of independent random variable is the adding of independent observations of the same random variable x. When you have a single random variable and two different observations are taken, and when we are adding these two observations, we are going to get another random variable which is w. So the equation can be written as w is equal to x1 plus x2. Next topic is mean and variance. We know that w is equal to x plus y, and if mean and variance of x and y are known, then you can calculate the mean and variance of w. First one is mean. We know that mean is denoted by expected value of w, which is equal to expected value of x plus y, where w is equal to x plus y. And if expected value of x equal to mu x and expected value of y is equal to mu y, then we can write mu w will be equal to mu x plus mu y. In the same way, the variance of w, that is sigma w square, is equal to sigma x square, that is the variance of x plus the variance of y, which is sigma y square. Here we have the proof for variance, that is sigma w square is equal to sigma x square plus sigma y square. In the LHS part, it is sigma w square. Then as per the definition of variance, we know that the variance is equal to expected value of the random variable w minus mean of the random variable mu w whole square. In the next line, we are going to substitute the value for w as well as the value for mu w. W is equal to x plus y and mu w is equal to mu x plus mu y. So when you substitute it, you are getting the expression to be expected value of x plus y minus mu x minus mu y the whole square. Now rearrange these terms, that is expected value of x minus mu x plus y minus mu y the whole square. Now expand this by using the formula a plus b the whole square. So you are getting the term to be expected value of x minus mu x the whole square plus 2 into x minus mu x y minus mu y plus y minus mu y the whole square. Now apply the expectation operator to each and every term over here. So the first term will be expected value of x minus mu x whole square. So expected value of x minus mu x whole square is nothing but sigma x square, that is the variance of random variable x. Now the second term is 2 into x minus mu x multiplied by y minus mu y. So this term is nothing but the covariance of random variable xy, that is 2 into covariance of xy, and the last term is expected value of y minus mu y the whole square, which is nothing but variance of y, that is sigma y square. Now since these two random variables are independent, x and y are independent, covariance of xy will be equal to 0. So when covariance of xy is equal to 0, the second term will be 0, and what you are going to get is sigma x square plus sigma y square. We have already calculated the mean and variance of the random variable w. Now we are going to find out what is the PDF and CDF of the random variable w, assuming that the CDF and PDF of the random variables x and y are known. The first case, what you are going to find out is CDF. We know that the basic equation for CDF is fx of x, which is equal to probability of x less than or equal to x. In the same way, we have to calculate the CDF of the random variable w, and the equation will be fw of w, which will be equal to probability of w less than or equal to w, and it can be rewritten as probability of x plus y less than or equal to w. The figure here shows an xy plane, and you can see a line wherein which x plus y is equal to w. This line, this particular line x plus y is equal to w, divides the xy plane into two different regions. A region where x plus y is less than w, and a region where x plus y is greater than w. Now to calculate the value of CDF, we are considering the region where x plus y is less than or equal to w. We know that w is equal to x plus y. Then fw of w, the CDF of w, would give the probabilities associated with that random variable. Therefore, we need to consider those x and y values whose sum is less than or equal to w, or alternatively when y is less than or equal to w minus x. Let the joint PDF of x and y be equal to fxy of x comma y. From this joint PDF, we can calculate the CDF by integration. That is, fw of w is equal to probability of w less than or equal to w, which is equal to integration from minus infinity to infinity, integral from minus infinity to w minus x, the limit is w minus x, fxy of x comma y dy dx. fxy of x comma y is the joint PDF. We have already calculated the equation for CDF. From the equation of CDF, now we are going to derive the equation for PDF. For that, take the derivative of CDF with respect to y and apply the limits, so that you will get the equation for PDF as fw of w is equal to integral from minus infinity to infinity fxy of x comma w minus x dx. Now, if x and y are independent to each other, then the joint PDF can be written as the product of individual PDF. Therefore, the equation can be rewritten as fw of w is equal to integral from minus infinity to infinity fx of x multiplied by fy of w minus x dx. The equation for PDF is fw of w is equal to integral from minus infinity to infinity fx of x multiplied by fy of w minus x dx. So this equation is in the form of a convolution integral. So you can write the equation in another format, that is fw of w is equal to convolution of fx of x and fy of y. Next topic what we are going to discuss is the characteristic function of a random variable w. This characteristic function is a topic which is covered in the first module, and it is given as an assignment. So I request you all to go through the materials shared. Now I'll just explain the equation related to the characteristic function. For a random variable x, the characteristic function is denoted by phi x of w, which is equal to expected value of e to the power j omega x, which is equal to integration from minus infinity to infinity. So this is just the expression for expectation. Integrate from minus infinity to infinity e to the power j omega x fx of x dx, where fx of x is the PDF of the random variable x. Now we can say that this characteristic function provides a sort of frequency domain representation of the random variable. Here we have to find out the characteristic function of the random variable w. Okay, for finding out the characteristic function of the random variable w, we know the PDF of the random variable w, which is fw of w, which is equal to integral from minus infinity to infinity fx of x fy of w minus x dx. Now applying in the main equation of the characteristic function, we get it as phi w of j omega is equal to double integral of fx of x fy of w minus x dx multiplied by e to the power j omega w dw. Now after changing the order of integration and replacing the variable w minus x by v, we are going to get the characteristic function of w, that is phi w of j omega is equal to phi x of j omega multiplied by phi y of j omega. Or in other words, I can say that the characteristic function of random variable w is the product of characteristic functions of the random variable x and y respectively. The next topic is independent and identically distributed IID random variables. In many applications, we are able to observe an experiment repeatedly. This sort of situation gives rise to independent and identically distributed random variables. In the last section, we derived expressions for the mean, variance, PDF and characteristic function for the sum of two independent random variables. The same method can be used when we are going to find out the sum of more than two independent random variables. Now let us consider a sequence of random variables x1, x2, x3, etc. up to xn, and these random variables are considered to be independent and identically distributed if the PDF associated with each xi is fx of x. Now we are going to find out the sum of IID random variables. As I told you before, we are considering a sequence of random variables starting from x1, x2, x3, etc. up to xn, and we are assuming that the PDF associated with each and every random variable is the same and it is equal to fx of x itself. Now we are going to find out the sum of these n number of random variables, and it can be written in this format, that is w is equal to summation of I is equal to 1 to n xi. Now as I told you, these are IID random variables, so their PDF will be same. If the PDF is same, then the mean and variance of each and every random variable will be same, that is expected value of xi will be equal to mu x, that is expected value of x1 equal to expected value of x2 is equal to expected value of x3, etc. is equal to mu x. In the same way, their variance will be also same, which is equal to sigma x square. Now if you are going to calculate expected value of xi multiplied by xj, then it will be equal to expected value of xi square if I and j are equal. So expected value of xi multiplied by xi will be expected value of xi square. Now as you all know, if expected value of xi square can be written as expected value of x square itself. Now this is nothing but the mean square value. Mean square value is equal to mu x square plus sigma x square from the definition of variance. Now we are assuming that I is not equal to j. If I is not equal to j, then expected value of xi xj can be written as expected value of xi multiplied by expected value of xj, because these two are independent random variables, so you can split and write it in this format. Therefore it will be equal to mu x into mu x, because the mean are same, mean of these random variables are same, so mu x into mu x, which is equal to mu x square. In the previous slide we have considered the general equation for w, which is equal to summation of xi. Now here we are going to consider some special cases. The first case is when n is equal to 2. When n is equal to 2, then you can write w2 is equal to the sum of only two random variables, that is x1 and x2. So as you all know, the expected value of w2 will be equal to expected value of x1 plus x2, and expected value of x1 is mu x and expected value of x2 is mu x. So expected value of w2 will be 2 mu x. Similarly, variance of w2 will be equal to 2 into sigma x square. The next case is when n is equal to 3. When n is equal to 3, by applying the same method, what we are getting is the expected value of w3 is equal to 3 into mu x, whereas the variance will become 3 into sigma x square. Now continuing in this way, we are going to get the equation for w is equal to wn minus 1 plus xn, and the same way the mean will be equal to mu w is equal to n into mu x, and sigma w square will be equal to n into sigma x square, as and when the value of n increases, the value of mu as well as value of variance will also increase. Now the characteristic function of the IID random variable, sum of IID random variable, is given by the equation phi w of j omega will be equal to phi x of j omega to the power n. So here you have a question to find out the mean and variance of z, where z is equal to summation I equal to 1 to 53 ui, and the random variable u has a mean of 0.3 and a variance of 1.5. Now as per the equation, we know that mu will be equal to n multiplied by e of u, which is equal to 0.3, and you are having the value 53 multiplied by 0.3, which is equal to 15.9. At the same time, variance will be equal to n multiplied by variance of u, which is 1.5, and you will be getting a value which is equal to 79.5.